How did oxygen nearly eradicate all life on Earth? Dear traveler, greetings. Today, we are about to dive into the depths of time, to an era when Earth was unlike anything we know, a silent planet without oxygen, dominated by strange seas and suffocating skies. But something is stirring there, an invisible upheaval, a change so profound that it will forever transform the history of the living. Where does this gas that upended everything come from? Why did it trigger one of the greatest biological cataclysms of all time? And how did life survive its own revolution? But before we embark on a new adventure, don't forget to like the video and subscribe to the channel to not miss anything. Thank you, and have a nice trip. Here we are, propelled 3.8 billion years, or 2.4 billion miles, back in time to the Archaean era. Earth, still unstable, already exhibits the beginnings of continents surrounded by primitive oceans. But it is especially its atmosphere that is surprising. Without free oxygen, it is dominated by dinitrogen, carbon dioxide, methane, and traces of carbon monoxide and dihydrogen. It was the volcanoes, particularly active at the time, which emitted large quantities of water vapor, carbon dioxide, and dihydrogen, explaining the primitive composition of the atmosphere. Meteorites and internal activity contributed to maintaining a reducing environment, thus poor in oxygen. Moreover, the sun only shone at 70% of its current intensity, which would have frozen the Earth without a compensating greenhouse effect. The climate warming of this period is mainly explained by two gases: carbon dioxide, released by volcanism and rock erosion, and methane, produced by early microorganisms. Both effectively trap terrestrial heat, with methane being particularly potent. Together, they prevented the planet from freezing, maintaining an average temperature sufficient for liquid water to persist over vast areas. Ancient geological formations offer us valuable clues about the anoxic atmosphere of this time. One of the most emblematic is the banded iron formations, these alternating layers of silica and ferrous minerals. At this time, the near-total absence of free oxygen in the oceans allowed iron, then present in dissolved and non-oxidized form, to combine with silica to form these characteristic deposits. Another key clue lies in reduced paleosols, these ancient soils formed without exposure to oxygen. Unlike current soils, rich in oxidized minerals due to the air, those of the Archaean retain an intact chemical composition without any trace of oxidative reaction. They testify to an atmosphere almost devoid of oxygen, offering researchers a valuable insight into conditions prevailing long before the Great Oxidation. On the biological front, the Archaean shows no trace of plants or animals as we know them today. Only microscopic organisms proliferate, living in warm aquatic environments. Bacteria and primitive cells exploit the chemical compounds present in the environment for nourishment. Flora and fauna, in the modern sense, are absent. Yet this microbial life broth already reveals an active biological chemistry, silently fermenting in the darkness of a world without oxygen. At this time, the weak sunlight combined with intense volcanism shaped a strange world. Continents were unstable, oceans vast and laden with mineral salts. Volcanoes continuously emitted steam, carbon dioxide, and sulfur compounds. Meteorites still fell regularly, sometimes altering the composition of the atmosphere. In the air, abundant methane reinforced the greenhouse effect alongside carbon dioxide, trapping heat near the surface. A fragile balance formed around water vapor. Volcanoes released it in large quantities, but thanks to the greenhouse effect, the temperature remained sufficient to avoid immediate condensation. The oceans then became a stable refuge, conducive to the emergence of organic chemistry. The lack of oxygen limited oxidation, favoring reactions essential to the appearance of life. In this silent context, Earth already harbored a microscopic biosphere, discrete yet foundational. The absence of free oxygen leads to significant consequences. Surface rocks do not oxidize as they do today, preventing the red or ochre hues typical of our era. Rivers carry more metallic ions, altering the chemical composition of marine sediments. In this oxygen-free world, microbes survive thanks to carbon dioxide and the fermentation of dissolved molecules. Life begins to organize in an entirely reductive environment. The Earth is still young, bathed in reducing gases, under a less intense sun than today. Yet, everything is set for great upheavals. Chemistry, geology, and life are balanced on a thread, heralding the arrival of free oxygen, which will transform the atmosphere, the oceans, and even the very surface of the globe. In the beginning, when the Earth was still just a mineral backdrop, its chemical activity took place mainly in the depths through volcanism. To understand the redox budget of this era, one must first grasp what a reducing environment is. It is a milieu low in free oxygen, but rich in hydrogen or sulfur compounds, capable of consuming oxygen if it appeared. We will dive into the primitive mantle to explore these reductive sources, noting the near-total absence of oxidizing agents on the surface. At this remote time, the Earth's mantle was considered slightly reducing. To better understand, scientists compare its chemical state to a reference called the iron-wustite buffer. The oxygen fugacity, that is, its ability to participate in reactions, was equivalent to what is called IW+1. In other words, the mantle contained a bit more oxygen than the reference threshold, but remained largely low in free oxygen compared to our current world. When we talk about the Earth's mantle, we often imagine molten rocks and extreme temperatures. During the Archaean, the depths of the mantle commonly exceeded 1,200 degrees Celsius or 2,992 degrees Fahrenheit, sometimes reaching much higher values. This heat, associated with a particular chemical composition, favored the release of reducing gases. At that time, volcanic activity was intense, as the Earth was still dissipating the heat accumulated during its formation. Among the gases resulting from volcanic degassing, two stand out for their reducing power: molecular hydrogen, or H2, and hydrogen sulfide, also known as H2S. The former, very light, tends to escape easily to the upper layers of the atmosphere. The latter, recognizable by its rotten egg smell, is toxic to most complex forms of life. At that time, these gases were not mere traces. They played a major role in preventing the accumulation of free oxygen in the atmosphere. Besides volcanism, another underground process released hydrogen, serpentinization. This term refers to a reaction between water and certain rocks of the mantle, rich in magnesium and iron silicates, like olivine. By penetrating these heated and fractured rocks, the water altered their mineral structure and produced hydrogen. These reactions, frequent in the Archaean, were particularly active at the mantle or ocean floor level. They gave rise to greenish scaly rocks called serpentinites, which also contributed to maintaining an oxygen-poor atmosphere. Now, let's look at the other side of the problem, the oxidant sinks. These denote environments capable of producing or maintaining free dioxygen, like today's forests or oceans via photosynthesis. But in the Earth's primitive era, there was neither vegetation nor forests, to transform carbon dioxide into oxygen. Only a few very simple microorganisms, perhaps installed near hydrothermal vents, occupied these hostile environments. The first photosynthetic cyanobacteria were not yet numerous enough or not yet efficient enough to release oxygen in quantity. As a result, the atmosphere remained largely devoid of free dioxygen. Imagine a primitive Earth where volcanoes continuously emit thick plumes of molecular hydrogen, hydrogen sulfide, and other gases rich in sulfur or carbon. Hydrogen, being highly reactive, immediately neutralizes any rare traces of nascent oxygen, preventing them from accumulating. Even if primitive algae or photosynthetic microbes tried to produce oxygen near the shores, this production was immediately consumed by the excess of reducing gases. Thus, no lasting stock of oxygen could form. The gas cycle revolved in a loop in a world dominated by reduction chemistry. The absence of oxidant sinks meant that no surface area was favorable for the emergence of animals or complex vegetation. Life was limited to a diversity of unicellular microorganisms, adapted to environments where oxygen was not involved. These anaerobic beings included bacteria living near underwater volcanic vents, using hydrogen sulfide and other chemical compounds to thrive. We were then far from having any fauna or flora as we know them today. There were only microscopic colonies scattered in the water, rock, and hot sediments. For a very long time, Earth functioned as a closed circuit for oxygen chemistry. On one hand, reducing compounds were constantly released by volcanism and internal reactions like serpentinization. On the other hand, almost no source produced enough oxygen to oxidize the environment durably. The rare attempts at local oxygenation were immediately neutralized by the excess of reducing gases. This imbalance kept the atmosphere in an anoxic regime without detectable free oxygen in the long term. Oxygenic photosynthesis marks a decisive turning point in Earth's history. Appearing over 3 billion years ago, when the atmosphere was almost devoid of oxygen, it was implemented by tiny organisms capable of capturing light to produce energy and release oxygen. This process slowly transformed the planet's chemistry, paving the way for a new biological era. These pioneers were cyanobacteria, also called blue-green algae. Originating from anoxygenic microbes using sulfur or hydrogen, they gradually learned to draw their electrons from water. With the help of light, they broke water molecules, releasing oxygen. This oxygen first accumulated in the oceans before reaching the atmosphere, marking the beginning of the Great Oxidation Revolution. At the core of the mechanism lies a complex cluster: 4 manganese atoms, 1 calcium atom, and 5 oxygen atoms. Buried in a protein structure, it extracts electrons from water and transfers them to the photosynthetic chain. This device converts light energy into chemical energy, making oxygenic photosynthesis possible. Initially, the oxygen produced in the first marine habitats remained very discrete. Cyanobacteria lived in stacked microbial mats, forming layers on shallow seafloors. In this microenvironment, oxygen almost immediately reacted with elements like reduced iron, disappearing before it could diffuse. Thus, it remained confined around the producing colonies without any real global impact at this stage. Beyond local phenomena, the isotopic signature of carbon provides a key indicator for dating the emergence of oxygenic photosynthesis. In some ancient sediments, a slight excess of carbon-13 is detected, an isotope heavier than carbon-12, less easily absorbed by living beings. This isotopic fractionation caused by photosynthesis leaves a measurable trace in rocks, revealing the early impact of this biological revolution. These slight enrichments in carbon-13 suggest that a mechanism of photosynthesis releasing oxygen already existed over 3 billion years ago. The evidence is found in ancient rock formations in Africa and Australia, where researchers have collected samples. The analysis of carbon, coupled with dating by radioactive isotope decay, has allowed for precise age determination. By studying these ancient crust fragments, researchers sometimes discover microstructures resembling bacteria, or even filaments similar to current cyanobacteria. The isotopic analysis of carbon reveals that they drew their carbon from inorganic sources to produce living matter. Fossilized in minerals, this biomass provides valuable evidence of photosynthesis at the origins of life. This observation is crucial. If it is possible to date these rocks and find an isotopic signature linked to photosynthesis, then it proves that the Earth already harbored oxygenic life forms long before oxygen began to accumulate in the air. These cyanobacteria lived in a radically different world, dominated by nitrogen, carbon dioxide, and methane. During the Archaean, the Earth received less solar energy than today, but greenhouse gases maintained a sufficient temperature. Cyanobacteria thrived in shallow waters, where they benefited from enough light while being partially protected from ultraviolet rays. The lack of oxygen did not bother them. They drew directly from water, an abundant resource, to fuel their metabolism. To understand the emergence of oxygen-producing photosynthesis, one must also look at genetics. Cyanobacteria gradually acquired genes that allowed them to optimize pigments like chlorophyll, as well as proteins capable of effectively capturing and transferring electrons. This evolution occurred in stages, starting from primitive forms of photosynthesis without oxygen. Once this strategy was mastered, cyanobacteria gained the advantage. Using water as an electron source provided them access to an abundant resource, unlike other microbes dependent on rare compounds. Their colonies multiplied in dense mats, comparable to tiny forests. By producing more and more oxygen, they altered the biosphere. This gas initially accumulated in the ocean and sediments. At the very dawn of Earth's history, more than 3 billion years ago, the planet offered a radically different landscape. Imagine a primitive shoreline, bathed in warm water around 30 degrees Celsius or 86 degrees Fahrenheit, under a sky veiled with volcanic ash. The atmosphere, low in oxygen and saturated with toxic gases, allowed in weakened light from a less bright sun than today. In these shallow waters, the first microbial communities organized themselves into thick layers, forming stromatolites. Stromatolites are laminated structures that are among the oldest evidence of life on Earth. To grasp the importance of stromatolites, it is necessary to understand that they are mineral structures, calcareous or siliceous, slowly created by colonies of microorganisms, often related to the earliest cyanobacteria. These bacteria practiced a primitive form of photosynthesis, capable of releasing oxygen. But the atmosphere, dominated by nitrogen, carbon dioxide, methane, or even carbon monoxide, immediately absorbed any produced oxygen. It was captured by other chemical compounds, present in both the water and air, preventing its large-scale accumulation in the atmosphere. When approaching the coastal stromatolites, one discovers small aquatic microenvironments where, under the effect of light, small amounts of dissolved oxygen begin to accumulate. These structures develop in shallow, well-exposed waters, ideal for photosynthesis. The microorganisms organized in layers-trapped sediments and used light to transform water and carbon dioxide into organic matter. This process released oxygen, which, even in very low concentrations, altered the immediate chemistry of the surrounding water. It is around the stromatolites that dissolved oxygen first came into contact with ferrous iron. present in large quantities in Archaean oceans. In the absence of oxygen, this iron remained in a reduced form, but as soon as a thin halo of oxygen appeared, it quickly oxidized into ferric iron, forming brownish particles that settled around the microbial colonies. These deposits mark the first traces of local oxidation on the Earth's surface. Thus, we witness true precipitations of oxidized iron, triggered by the occasional presence of oxygen. Ferrous iron reacted at the slightest contact with this gas, turning coastal areas into natural laboratories. Each molecule of produced oxygen was immediately used to oxidize the iron. The formed hydroxides, although unstable, could stabilize into solid minerals upon contact with sediments, leaving a lasting trace of these localized reactions. Why didn't the oxygen produced around the stromatolites spread more widely? Quite simply because it was immediately neutralized by the environment. At that time, the atmosphere and the oceans were saturated with reducing gases that would instantly react with the oxygen. It was like a constant chemical battle where each oxygen molecule was intercepted before it could escape. However, this discrete process played a crucial role in the evolution of the planet. In these coastal areas, photosynthetic bacteria were laying the first stones of oxygenation. Long before the sky turned blue or the oceans teemed with complex life, Earth's chemistry was changing. The thin red layers of iron-rich sediments preserved in rocks bear witness to this inaugural phase, heralding the Great Oxidation. These coastal microenvironments also allowed some microorganisms to gradually acclimate to slightly oxidizing conditions. At that time, life was limited to single cells, with no animals or plants. Yet these tiny beings, capable of photosynthesis, were already preparing the future. Faced with dioxygen, both a resource and a toxin, they developed enzymatic systems to protect themselves, a sign of slow evolutionary pressure. In this ancient landscape, the rapid precipitation of oxidized iron locally colored the sediments. Around the stromatolites, in shallow waters, reddish bands appeared, contrasting with the gray or greenish deposits, reflecting chemical variations. For geologists, these colors are valuable markers. A thin, reddened layer can indicate a brief oxygen excess over the neutralization capacity of iron, or methane. Thus, this pivotal era reveals how, thanks to simple microscopic organisms, Earth's chemistry began to evolve. The dioxygen, however fleeting it was, left a lasting imprint in the rock by associating with iron. This subtle signal, emerging in the shadow of stromatolites, initiated a profound upheaval. There, sheltered from external turmoil, microbial life was already experimenting with the power of photosynthesis. And without knowing it, it was slowly preparing the world to breathe. At the bottom of ancient oceans, between 3.2 and 2.5 billion years, or 2 billion and 1.5 billion years BCE, astonishing deposits called banded iron formations were formed. These rocks, composed of alternating bands of dark iron and light silica, form a true visual record of Earth's history. At that time, the atmosphere and the oceans were almost completely devoid of dioxygen, keeping iron in its reduced form. In these ancient seas, iron circulated mainly as ferrous iron, iron 2+, soluble in oxygen-poor water. This lack of dioxygen prevented its oxidation. Conversely, ferric iron, iron 3+, more oxidized, formed solid particles that settled on the bottom. This difference shows how much the presence of oxygen altered the ocean chemistry of the time. In these ancient waters lived primitive bacteria, some of which practiced photosynthesis. They produced a bit of oxygen, but it never lasted long. As soon as it appeared, it reacted with ferrous iron, which oxidized to ferric iron. This phenomenon, known as the titration of the first dioxygen, prevented oxygen from accumulating in the atmosphere. As soon as dioxygen came into contact with dissolved ferrous iron, it triggered a reaction. The iron oxidized and formed oxides or hydroxides of ferric iron, insoluble. These particles fell to the seabed, accumulating in red layers. Over time, alternations between iron and silica deposits created these colored bands, a true memory of each small chemical shift toward oxidation. In this extreme environment, only bacteria and archaea capable of surviving hostile conditions existed. Yet these tiny organisms profoundly modified Earth's chemistry. Their metabolisms, particularly the production of dioxygen, triggered lasting geological transformations. They are the distant ancestors of all current life. The banded iron formations illustrate the deep link between life and the mineral world. Formed between 3.2 and 2.5 billion years, or 2 billion and 1.5 billion years BCE, they are now found in Australia or North America. Through techniques like mass spectrometry, scientists trace how the ocean regulated the nascent dioxygen. This constant oxidation process, transforming iron 2+ into iron 3+, trapped vast amounts of locally produced oxygen, preventing it from reaching the atmosphere. According to scientists, these deposits may have captured up to 1019 to 1020 moles of oxygen. This represents a sextillion molecules, a colossal sink for dioxygen. Beyond the abundance of these deposits, this estimate of the ferric sink reveals the scale of geochemical reactions of the time. Each time microbial mats released a bit of dioxygen, the ocean reacted almost instantly, trapping the oxygen. This natural mechanism slowed the oxygenation of the atmosphere and initiated the very first redox cycle of the Earth. What is striking is the fragility of this balance, maintained for hundreds of millions of years. At the heart of the primitive Earth, a slow internal cooling begins. Although much more discrete than surface temperature variations, this process plays a key role in planetary dynamics. The heat gradually escaping from the core and mantle fuels volcanism, essential for the release of gases and nutrients critical for the emergence of life. At this time, terrestrial volcanism is said to be ultramafic, as it produces lavas rich in iron and magnesium. These lavas come from a still very hot mantle, capable of melting rocks at extreme temperatures. The volcanoes emitting this type of lava often form komatiitic deposits, named after the rocks called komatiites. But as the Earth cools, these ultra-hot lavas become rarer. This evolution marks a turning point. Geological activity becomes slightly less intense, with volcanic flows losing power and heat. In this changing context, the progressive decrease of ultramafic volcanic eruptions has major consequences on the atmosphere and oceans. The ancient eruptions, rich in iron, magnesium, and dihydrogen, H2, become rarer. The gases emitted by the mantle, previously dominated by oxygen-reactive molecules, also decrease. This evolution reduces the pressure of the so-called reducing flows, meaning the amount of substances capable of capturing oxygen. These compounds, also known as reducing equivalents, include notably the dihydrogen released by volcanoes. Their scarcity facilitates the appearance and accumulation of nascent oxygen in the waters and the atmosphere. In the long term, this simple decrease in volcanic activity will play a decisive role in the progressive enrichment of the planet in oxygen. The transition from komatitic lavas to more oxidized basalts is explained by a drop in mantle temperature. The komatiites, which emerged at more than 1500 degree or 27th and 32 degree, gradually gave way to somewhat cooler lavas around 1200 degrees or 2192 degrees. This decrease, seemingly modest, reduces the magma's ability to dissolve and transport certain gases. Dihydrogen, notably, escapes in smaller quantities, while more oxidized gases like carbon dioxide tend to stay longer in the magmatic fluids. These are referred to as oxidized lavas because they contain fewer elements capable of capturing atmospheric oxygen. At this time, some microbial niches are already exploiting the discrete presence of free oxygen to metabolize nutrients more efficiently. Even rudimentary microscopic life starts to benefit from a less hostile and more stable chemical environment. Another major turning point of this era is the appearance of the first large-scale subduction zones. This phenomenon occurs when two tectonic plates collide and one sinks under the other, plunging into the mantle. This movement promotes the recycling of chemical elements, notably the transformation of sulfide into sulfate, its more oxidized version. When sediments rich in sulfides are drawn into the subduction, the high pressures and temperatures facilitate this conversion to oxygen-enriched compounds. In the volcanic arcs located near these zones, more oxidized sulfur gas emissions are observed, indicating an internal chemistry less favorable to reducing gases. As subduction becomes permanent and the Earth's crust thickens, new mountain ranges emerge, altering the climate and natural habitats. Over the long term, this geological dynamic transforms biodiversity. In coastal areas, ancient microbial communities adapt their survival mechanisms to a more stable environment. The first mats of photosynthetic microorganisms spread in shallow waters, sheltered from lava flows. The decrease in dihydrogen degassing reduces the chemical aggressiveness of the atmosphere, facilitating carbon dioxide fixation by these organisms. In hydrothermal oases, extremophile archaea continue to draw their energy from hot fluids. However, environments with high reducing potential become rarer, pushing some life forms to innovate metabolically. Meanwhile, the increased production of sulfate at the edges of volcanic arcs reorganizes the cycles of sulfur, iron, and manganese. This chemical evolution sets the stage for future oxygenation. As the Earth cools, it sheds its reducing forces, initiating a profound environmental and biological transition, whose effects will only fully reveal themselves over the course of eras. As primitive Earth continued its evolution, oxygen remained almost absent from the atmosphere. Yet, in the shallow seas, some photosynthetic microorganisms were already beginning to produce it. This emergence, however, remained invisible because the free oxygen was immediately captured by very reactive compounds, notably minerals rich in iron and sulfur. These true chemical traps, known as ferruginous sulfurous sinks, played a key role in preventing the accumulation of oxygen in the environment. These ferruginous sulfurous sinks captured oxygen as soon as it formed, through spontaneous chemical reactions. Ferrous iron, dissolved in water, transformed into ferric iron, while sulfides oxidized into sulfates. With each bond between oxygen and these elements, some of the free oxygen disappeared, slowing its accumulation in the atmosphere. Even though its production slowly increased, its concentration remained extremely low. Over time, the balance of redox reactions slowly evolved at the Earth's surface. Ultramafic volcanism, which released large amounts of reducing compounds like dihydrogen, began to decline. This decrease meant that less nascent oxygen was mobilized to neutralize volcanic gases. At the same time, photosynthetic microorganisms, stimulated by an abundance of nutrients, intensified their oxygen production, although it remained modest compared to the high chemical demand of the surrounding minerals. Gradually, the oxygen demand from the ferruginous sulfurous sinks diminished. Surfaces saturated with ferrous iron and sulfides could no longer indefinitely absorb the additional oxygen. In some coastal environments, thin layers of iron oxides began to form, signs of a first local accumulation of dissolved oxygen. But on a planetary scale, this progression remained still invisible. The partial pressure of oxygen remained very low compared to current levels. In this context, researchers speak of latent partial pressure of oxygen. Oxygen was indeed being produced, but its impact remained invisible, absorbed by the many chemical sinks. No immediate disruption of the atmosphere was felt. On the surface, Earth still seemed devoid of oxygen. Yet, behind the scenes, small quantities began to accumulate, sketching a slow tremor in this still nearly anoxic world. The slow rise of oxygen in the atmosphere owes much to photosynthesis. This process allows unicellular microorganisms to capture solar energy and convert it into chemical energy. Through specialized pigments, they decompose water, release oxygen, and fuel their metabolic chains. Fossil evidence suggests they formed vast microbial mats in marine environments, leaving behind thin layers of oxidized iron. Over tens of millions of years, this activity eventually profoundly transformed the composition of the atmosphere. Current numerical models aim to reconstruct this shift using isotopic chemistry and residual traces in ancient rocks. According to estimates, it was about 2.7 billion years ago that the oxygen fluxes produced by life began to match, then surpass, those of reducing gases. In other words, for the first time, the amount of oxygen released compensated for that absorbed by ferrous iron, sulfides, and other natural reactive components. The transition from an oxygen flow lower than that of reducing gases to an equilibrium marks a major milestone in Earth's history. Until then, every molecule of oxygen produced was immediately neutralized by geochemical sinks. Thereafter, although most of the oxygen was still absorbed by oxidation reactions, slight surpluses began to appear. This surplus, though subtle, gradually allowed for the emergence of organisms more tolerant to oxygen. This can be seen as the starting point of a slow but irreversible atmospheric revolution. In geology, this transition towards equilibrium between dioxygen and reducing agents marks the foundation of a new planetary dynamic. After 2.7 billion years, many sedimentary basins reveal an increase in traces of ferric iron and sulfates, indicating that a greater amount of oxygen was circulating in certain environments. The atmosphere remained low in oxygen, but already the promise of an oxygenating world was emerging, albeit timidly. Paleosols, ancient fossil soils, also provide valuable clues. Before this transition, these soils appear in a reduced state, indicating an environment almost devoid of oxygen at the time of their formation. After this critical threshold, traces of oxidation become more frequent, indicating that the oxygen content, though still low, was enough to modify surface chemistry. This data confirms that the balance between oxygen production and consumption had finally shifted. At this distant time, the Earth bore no resemblance to the one we know today. The atmosphere was saturated with carbon dioxide and received an increasing supply of methane, now recognized as one of the most potent greenhouse gases. To comprehend this evolution, one one must delve into the unseen world of oxygen-deprived marine sediments. Buried in these dark muds lived methanogenic archaea, microorganisms capable of producing methane by decomposing organic or inorganic matter. These beings thrived in environments completely devoid of molecular oxygen. The production of methane in these deep sediments is called methanogenesis. The methanogenic archaea drew their energy by exploiting the chemistry of carbon. Some converted hydrogen into methane, while others broke down more complex molecules to produce this gas. At the time, microbial activity in the seabeds and primitive marshlands was the main natural source of methane, much more than volcanoes, which emitted little. The near-total absence of complex animals also meant that no organism was there to consume this methane once released into the air, favoring its rapid accumulation in the atmosphere. As methane reached the surface, it profoundly altered the primitive climate. This gas, much more powerful than carbon dioxide at trapping heat, formed a genuine thermal blanket around the planet. At the time, the sun was less luminous than it is today, and this insulating role of methane, reinforced by carbon dioxide, became crucial in maintaining a temperature sufficient for the presence of liquid water. The oceans, inhabited by microorganisms, thus remained at average temperatures of some dozens of degrees or tens of degrees Fahrenheit, creating a warm and humid environment favorable to life. Methane not only acted as a thermal blanket, it also formed a partial filter against the most intense ultraviolet rays. These rays, by interacting with water vapor in the upper atmosphere, can break its molecules, a process called photodissociation. It sometimes releases hydrogen and, indirectly, dioxygen. But in excessive concentration, methane attenuates this radiation, thus limiting the decomposition of water and the production of oxygen by this route. While this protection benefited microorganisms sensitive to UV, it also slowed down a secondary source of oxygen, just as photosynthesis was starting to emerge without yet dominating. The high concentration of methane gave rise to an important phenomenon, photo-oxidation. This process refers to the attack of methane molecules by reactive agents generated under the effect of sunlight. When photons, particles of light, strike the atmosphere, they can break certain molecules, producing radicals. Radicals are unstable fragments, equipped with unpaired electrons, ready to react. In the case of methane, these reactions generate oxygen-rich radicals, called pre-oxidants, which then begin to spread in the primitive atmosphere. These reactive pre-oxidants initiate chain reactions, gradually altering the chemical balance of the atmosphere. They can transform certain sulfur or nitrogen compounds into more stable oxides, contributing to the gradual appearance of more oxidized products. Although limited initially, this dynamic initiates a shift towards a less reductive environment. The atmosphere becomes progressively more complex, with the formation of byproducts such as nitrogen oxides or peroxides resulting from reactions between methane, nascent oxygen, and other elements. These molecules, true building blocks of planetary chemistry, transform the upper atmosphere into a veritable evolving laboratory. Despite the rise of photochemical reactions and the production of pre-oxidants, the impact on the free oxygen content remained very limited. The Earth had neither forests nor an abundance of algae capable of massively producing oxygen. Cyanobacteria, having barely appeared, were just beginning their photosynthetic role. The continents were almost entirely bare, as no terrestrial plants yet existed. As for the fauna, it was limited to a few marine microorganisms and rudimentary bacterial mats. At this stage, oxidation was essentially based on chemical reactions, among which the photo-oxidation of methane was only one component. The elevation of methane relative to carbon dioxide had lasting climatic effects. On one hand, the greenhouse effect warmed the planet beneficially. On the other, this imbalance changed the way the atmosphere filtered solar radiation. Some researchers believe these variations led to noticeable changes in the global average temperature. In some areas, shallow seas may have dried up or reached several tens of degrees, 86 to 122 degrees, while other regions further from the equator remained noticeably cooler. The accumulation of methane in the air triggered a cycle of feedbacks. Its photo-oxidation generated particles that could, to some extent, bind with oxygen. Although these quantities remained low at this stage, they were already initiating a complexification of atmospheric chemical reactions. These successive chains, difficult to observe in rocks, nonetheless leave isotopic clues and traces of fractionation in sediments. These marks allow researchers to conclude that the photo-oxidation of methane contributed, discreetly but surely, to the slow rise of oxygen. In this aquatic and volcanic world, devoid of trees or complex terrestrial plants, life was limited to microscopic communities. By multiplying in various niches, they benefited from the temperate climate maintained by the greenhouse effect. Methanogenic archaea continued to enrich the atmosphere with methane, feeding photochemical reactions. This coexistence between anoxic life and atmospheric chemistry under solar influence reflects an unstable balance. Methane, stimulated by microbial activity, formed the link between the mineral world and the living, influencing the climate, light, and the formation of key radicals for chemical evolution. The increase in the methane to carbon dioxide ratio shaped both the climate and the chemistry of the primitive Earth. In the shadows, anoxic sediments, cradles of methane production, continued their activity, while the atmosphere enriched with greenhouse gases and oxidant precursors. These interconnected elements initiated, over hundreds of millions of years, a gradual transformation of the planet, gradually leading it towards the more familiar conditions we know today. At the beginning of Earth's history, long before the emergence of complex biodiversity, the atmosphere was unrecognizable. Dominated by carbon dioxide, it also contained methane and dinitrogen, while a less intense sun flooded the planet with powerful ultraviolet rays. In this context, atmospheric chemistry was already beginning to evolve. Little by little, these radiations triggered catalytic reactions capable of breaking molecules and recomposing oxygen, initiating the formation of a thin ozone layer, a future vital barrier for life's protection. Photolysis, the decomposition of a molecule under the effect of light, plays a key role in this context. When ultraviolet rays hit a carbon dioxide molecule, they can split it into carbon monoxide and an oxygen atom. Even though this reaction is inefficient, its constant repetition under sufficiently intense light ends up producing a reserve of oxygen atoms. Over time, these atoms can recombine to form dioxygen in the upper layers of the atmosphere. Derived from the decomposition of carbon dioxide, the oxygen atom is extremely reactive. In the high layers of the atmosphere, where the pressure is low and collisions are rare, some of these solitary atoms end up bonding with diatomic oxygen molecules already present in small quantities. These recombinations can generate more dioxygen, or sometimes intermediates that evolve into ozone. Through countless slow reactions, a slight accumulation of molecular oxygen thus begins to appear in the stratosphere. The photolysis of carbon dioxide is not the only mechanism of oxygen production at this time. Some rudimentary biological processes also began to release it, but in a very localized manner. On the other hand, for the formation of the ozone layer, ultraviolet rays play a central role. By regularly fragmenting carbon dioxide, they maintain a small reservoir of oxygen atoms. Although the amount produced remains small on a global scale, it acts as a catalyst in the upper layers of the atmosphere. The formation of ozone relies on the simultaneous presence of dioxygen and free oxygen atoms in the stratosphere. Under the effect of ultraviolet rays, a molecule of dioxygen can break apart, releasing atoms capable of associating with other molecules to form ozone. This molecule, composed of 3 oxygen atoms, is unstable but essential. It absorbs the most harmful UV radiation. Thus, primitive Earth begins to equip itself with a protective shield, paving the way for more life-friendly conditions. Although very thin and limited to high altitudes, the nascent ozone layer already represented a major advance for primitive Earth. Without even partial protection against ultraviolet rays, the tiny unicellular organisms would have been constantly exposed to mutagenic radiation. The appearance of this barrier, tenuous though it may be, marked a first step toward a less hostile environment. As free oxygen atoms multiplied, mechanisms for the creation and destruction of ozone came into play. This gas forms by associating an oxygen atom with a dioxygen molecule under the effect of ultraviolet rays, but it can also be destroyed by these same rays. The balance, therefore, depends on both the intensity of solar radiation and the amount of dioxygen present. Even at low concentrations, the ozone layer profoundly modifies the distribution of radiation, offering essential protection. At high altitudes, where the air is extremely rarefied and temperatures well below freezing, ultraviolet rays strike with intensity. It is in this environment that the first major chemical transformations occur. The appearance of a thin ozone shield then allows for the absorption of an increasing share of harmful radiation before it reaches the lower layers. Although very far from the current density, this thin stratospheric layer initiates a subtle but crucial change in Earth's capacity to protect its surface. At this stage, the future ozone layer does not yet cover the entire planet, but an initial outline forms in the high atmosphere. Under the constant effect of ultraviolet rays, the photolysis of carbon dioxide continues to release oxygen atoms, allowing occasional ozone formation. This thin veil initiates the birth of a true planetary shield. Over time, with the arrival of other sources of oxygen, the concentration of dioxygen and ozone will slowly increase, laying the foundation for a mechanism essential to the evolution of life. At the surface, these changes remain almost imperceptible, but in the skies, a turning point is occurring. For the first time, sunlight begins to be filtered, heralding a more clement future. At the origins of the Earth, the isotopic composition of sulfur is one of the most revealing indicators of the evolution of the atmosphere and microbial life. At that time, the air was almost devoid of oxygen, and the planet experienced intense volcanic activity. To study these ancient environments, researchers rely on a key indicator. This is delta 33S, which measures the relative abundance of sulfur isotope 33 compared to isotopes 32 and 34. This signal reveals so-called mass-independent fractionation, that is to say, unexpected deviations from the usual laws of isotopic chemistry, a valuable indication of unique atmospheric processes at that time. Before going further, it is necessary to clarify what is meant by mass-independent fractionation. Normally, the isotopes of an element are distributed according to their weight. The lighter ones react faster, following well-established mathematical laws. But in some ancient samples, geologists have observed delta 33S values greater than +2% of zero, abnormal deviations that cannot be explained solely by the difference in mass. This type of fractionation arises from rare photochemical reactions, notably the dissociation of sulfur dioxide under intense radiation, a phenomenon difficult to reproduce in the current atmosphere. These Delta 33S anomalies appear mainly in rocks dating back more than 2.45 billion years, or 2,700,000 miles, a time when life on Earth was limited to simple microbial forms. Oceans then harbored bacteria, exploiting rudimentary chemical reactions to survive. No plants or animals in the modern sense existed yet. However, mats of microorganisms sometimes covered shallow lagoons, forming structures called stromatolites. These discrete colonies housed bacteria capable of slow transformations, notably related to the sulfur cycle. In the primitive atmosphere, sunlight interacted with sulfur dioxide released by volcanoes. This radiation broke the chemical bonds of the molecule, generating fragments capable of recombining in various ways. This is how unusual isotopic signatures are formed. Some radicals preferentially incorporate sulfur isotope 33, creating a mass-independent fractionation. The sedimentary rocks of this era then reveal delta 33S values greater than +2% 0. This is evidence that the atmosphere at that time allowed extreme reactions, impossible under current oxygen-rich conditions. Around 2.45 billion years ago, or 2,700,000 miles, the Delta 33S anomalies abruptly disappear from the geological records. This shift marks what scientists call the Great Oxidation Event, or GOE. It designates the period when Earth's atmosphere became enriched with oxygen on a planetary scale. From an isotopic perspective, this is a major turning point. Before this date, mass-independent fractionation is common in Archaean rocks. After, it becomes almost non-existent, as if the sudden appearance of a chemical barrier, linked to oxygen, prevented the formation of these atypical signatures. This upheaval is explained by the fact that beyond a certain threshold of oxygen in the air, the photolysis of sulfur dioxide no longer generates as many free radicals. The now abundant oxygen reacts with sulfur compounds, limiting their ascent to the upper layers of the atmosphere, where ultraviolet rays are most intense. As it travels through the atmosphere, oxygen is also transformed into ozone, which further filters these rays. The consequence: sulfur dioxide molecules are less exposed to atypical ruptures, and Delta 33S anomalies drop sharply. Researchers estimate that a partial pressure of oxygen equivalent to 10 to 5, or 0.0032% of the current level, was enough to block the transport of photolyzed sulfur dioxide. In other words, a tiny fraction of the oxygen we breathe today was already enough to disrupt the sulfur cycle and erase the ancient isotopic signatures in the sediments. As small as it may be, this concentration represented an immense change for a planet previously dominated by gases like dihydrogen and carbon dioxide. For microbial life, even a moderate increase in oxygen represented both a challenge and an opportunity. At that time, many microbes used sulfur in their metabolism, oxidizing or reducing it according to their energy needs. The disappearance of Delta 33S anomalies also reflects a reorganization of these networks. Some lineages learned to tolerate oxygen by developing protective mechanisms, while others disappeared from surface environments. Gradually, the microbial communities, predominant on Earth, specialized in new metabolic pathways, taking advantage of this increasing presence of oxygen. Geologically speaking, the disappearance of mass-independent fractionation after 2.45 billion years is one of the most reliable markers of the Great Oxygenation Event. By analyzing deposit thickness and sulfur isotopic composition, geochemists can accurately pinpoint the moment when the atmosphere crossed a critical threshold. Before this date, the air remained largely anoxic, allowing intense photolysis of sulfur dioxide at high altitudes. Afterward, the increase in oxygen made this process much rarer, leading to the disappearance of high delta 33S values in subsequent rocks. In certain sedimentary basins, the geological layers between older and more recent formations clearly show the transition. Delta 33S values drop within a few million years. Species dependent on a reducing environment are pushed deeper, while those capable of tolerating oxygen begin to thrive. This shift initiates an evolutionary trajectory that, much later, will pave the way for the diversification of more complex life forms. The sudden disappearance of mass-independent fractionation anomalies in sulfur isotope 33 serves as a key indicator of atmospheric evolution. From this point on, the atmosphere contains enough oxygen to modify planetary chemistry and influence the distribution of microorganisms. This upheaval prepares the biosphere for more stable conditions enriched with oxygen, gradually fostering the emergence of more complex life forms. Although animals and plants will appear much later, their future is already being shaped by these subtle isotopic changes. This chronology tells, in its own way, the birth of a changing Earth, soon ready to host a thriving biodiversity. Let's go back about 2.445 billion years to a pivotal time when the famous banded iron formations, or BIFs, began to give way to massive hematite deposits. To understand this transition, let's imagine an ancient marine landscape. Shallow areas alternate with deeper waters. In well-lit coastal regions, vast microbial mats thrive. Composed of photosynthetic bacteria, these organisms produce oxygen. But at that time, this gas does not yet dominate the atmosphere. It remains confined to local scales, dissolves in water, and is quickly captured by ferrous iron, a highly soluble ion present in these environments. To better visualize this era, imagine a distant volcanic landscape. Islands emerge from a still young ocean, bordered by solidified lava flows. Sporadic eruptions release gases into the atmosphere, some of which dissolve in the waves or settle on the shores. The Earth remains warm, with an average temperature above 68 degrees Celsius, 20 degrees, although variable depending on the region. Meanwhile, tectonics slowly drift the earliest continents, locally altering water depth and hydrothermal activity. These changes directly influence the chemical balance of the seas, particularly how iron dissolves or deposits. For hundreds of millions of years, banded iron formations accumulated in successive layers in ancient oceans. These formations are distinguished by alternating red or brown bands rich in iron and lighter layers of silica. They result from a process where ferrous iron, dissolved in water, reacted with small amounts of oxygen locally produced by photosynthetic bacteria. This mixture slowly precipitated, forming regular strata on the seabed. But around 2.445 billion years, this cycle halts. BIFs become rare and give way to more massive deposits rich in hematite and jasper, oxidized minerals that attest to an atmosphere in transition. Hematite is an iron oxide where iron appears in ferric form, Fe3+, soluble in water. The analysis of massive hematitic deposits shows that at this time, seawater already contained enough dissolved oxygen to transform ferrous iron into ferric iron, which is insoluble. Jasper, often associated with hematite, is a colored silica that reflects the peculiar chemical environment in which these minerals precipitated together. These rocks, sometimes polished by erosion, are evidence of a major transformation in the iron cycle in the oceans. The decline of ferrous iron leads to a cascade effect. The classic iron bands, with their alternating layers of silica and ferric minerals, cease to form. In their place, vast, massive deposits of hematite appear. If we dove into these ancient waters, now capable of transporting oxygen over greater distances, we would observe impressive reddish sheets of iron oxides mingling with silica. This would give birth to spectacular rock formations with intense red hues, sometimes marbled with dark or light shades. Under the microscope, the oxidized iron crystals unequivocally testify to the rise of oxygen in the water. The ocean can no longer retain as much dissolved ferrous iron. Previously, iron bands formed in a low oxygen environment where every trace of oxygen was immediately locally consumed. The BIF recorded this alternation between available iron, oxygen peaks, and precipitation. But as soon as oxygen diffuses more widely, iron is oxidized continuously and transforms into stable minerals, giving rise to massive hematite deposits. Beyond the chemistry of iron, this change has a major impact on the biosphere of the time. Even without complex fauna or flora, photosynthetic microorganisms evolve in these rapidly changing environments. The increasing oxygen opens up new niches for them and allows some to develop more efficient respiration modes. Others, more sensitive to oxidation, must protect themselves or retreat to areas still poor in oxygen. Hematite deposits then become the reflection of a global upheaval where the chemistry of the oceans reorganizes and shapes primitive life. To better grasp this shift, think about the solubility of iron. Iron 2+ remains dissolved as long as the water contains little oxygen. But as soon as this gas becomes more present, its solubility collapses. That's why the iron bands, witnesses of a balance between oxygenated and anoxic environments, gradually disappear. The process becomes more constant, more direct, favoring the formation of rocks rich in hematite. Researchers have shown that the dissolved oxygen in water does not come solely from chemical reactions in the atmosphere, but mostly from photosynthetic microorganisms. By using light to transform carbon dioxide and water into organic matter, they release oxygen. As this release accumulates, it prevents iron 2+ from remaining in solution. The oceans then shift from an anoxic state to an increasingly oxygenated state, marking the end of iron bands and the start of massive hematite and jasper deposits. Between 2.47 and 2.43 billion years ago, the Earth experienced a significant phenomenon, the episode of transient oxygen. During this interval, the share of oxygen in the air jumps dramatically, from almost nothing to 1 to 3% of today's level. This may seem low, but at the time, it was a revolution. Oxygen was still rare, and this sudden surge marks a major turning point in the atmospheric history of the planet. To understand the importance of this rise, we must return to the composition of the ancient atmosphere. Before the transient episode, gases like carbon dioxide and methane prevented any lasting accumulation of oxygen. Cyanobacteria did produce oxygen through photosynthesis, but it was immediately absorbed by reducing compounds, notably volcanic dihydrogen. Then, between 2.47 and 2.43 billion years ago, this fragile balance suddenly broke. On the Cap Val Craton in southern Africa, fossilized soils show chemical weathering marked by iron oxides, indicating there was already enough oxygen in the air to oxidize minerals. They suggest a partial oxygen pressure equivalent to 1 to 3% of the current level. To explain this phenomenon, specialists point to the crossing of a critical oxidant threshold. As long as the oxygen produced by photosynthesis was neutralized by reducing gases, the atmosphere remained almost devoid of free oxygen. But once the production of oxygen exceeded trapping capacities, the surplus could accumulate. This tipping point explains how a slight imbalance led to a rapid, although temporary, increase in oxygen levels. One of the key factors in this amplification effect is the drop in atmospheric methane. This gas, produced notably by methanogenic archaea, is very effective at trapping heat. But when oxygen becomes more abundant, it reacts with methane to produce carbon dioxide and water, thus reducing the atmosphere's ability to warm. This temperature drop decreases water vapor and disrupts climate dynamics, also influencing volcanic activity and the release of hydrogen, another consumer of oxygen. At that time, Earth received only 70% of today's solar light. Thus, any decrease in greenhouse effect related to the decline in methane had a marked impact on temperature. The cooling led to the expansion of ice, increasing the reflection of solar radiation and further accentuating the drop in temperatures. Simultaneously, quieter volcanic activity emitted less hydrogen, which limited oxygen consumption. These chain reactions allowed oxygen to briefly flourish. However, this oxygen surge, between 1% and 3% of the current level, was insufficient to allow the emergence of complex life. No multicellular organisms were yet present. The biosphere was limited to bacteria, archaea, and a few primitive marine eukaryotes. Despite this low diversity, the episode transformed surface chemistry, initiating a long process toward a more oxygenated Earth. But this state did not last. After a few tens of millions of years, the oxygen pressure probably receded due to a rebalancing effect. Reductive materials from the mantle, rock weathering, and biosphere dynamics closed the gap. Still, this brief rise in oxygen left the trace of oxidized paleosols on the Cap Vale, a valuable witness. The Huronian glaciations represent a major climatic episode that occurred nearly 2.4 billion years ago. Their traces are found in three sedimentary layers called tillites, which witnessed the dramatic advance of ice into regions that were once temperate. These deposits, successively named Makganyeni, Royhoogte, and Timeball Hill, range from 2.45 to 2.2 billion years ago. They result from the accumulation of glacial sediments deposited during the progression, and then the melting of glaciers. The term tillite refers to a consolidated rock resulting from the action of an ancient glacier. It contains a heterogeneous mixture of gravel, pebbles, or blocks, trapped in a fine matrix typical of active glacial transport. At that time, Earth's climate was undergoing profound upheavals, notably because of the drop in methane. This simple compound helped maintain mild temperatures by retaining heat emitted by the ground. But as it oxidized to become carbon dioxide, its warming effect gradually decreased. Although carbon dioxide contributes to the greenhouse effect, it retains heat less efficiently than methane. As a result, the planet began to cool. This global cooling favored the expansion of vast ice caps, including near the geological equator of that time. The glaciers caused significant variations in sea levels and disrupted the environment. The three identified glacial horizons each present typical tillite deposits. The word horizon here refers to a well-defined rock sequence, marking a distinct glacial period. These formations, all located in South Africa, each have their own sedimentary and geochemical characteristics. The decrease in atmospheric methane and its oxidation into carbon dioxide profoundly altered Earth's thermal balance. As dioxygen gained ground, more methane was converted, decreasing the greenhouse effect. This change triggered a chain reaction that favored the expansion of ice, explaining the emergence of the Huronian glaciations. A key factor in the Huronian glaciations is albedo, the ability of a surface to reflect sunlight. Snow and ice, being very bright, reflect a large part of the radiation received. Thus, as glaciers expand, the albedo increases, reducing the energy absorbed by the Earth. This mechanism further reinforces cooling and promotes the expansion of ice sheets, these immense continental glaciers. These vast ice sheets also promote carbon sequestration in the form of buried sediments and organic matter. During glacial periods, some carbon is stored in frozen marine or lacustrine beds, limiting its return to the atmosphere. This leads to less circulating carbon dioxide and a slight relative increase in dioxygen. This slight rise in dioxygen triggers a new positive feedback. The more abundant oxygen becomes, the more it transforms residual methane into carbon dioxide, further reducing the greenhouse effect. This virtuous cycle of cooling stretches over several tens of millions of years, leading to a long glacial period. The life forms of the time, mainly primitive microbes, must then adapt to an increasingly hostile world, where even the growth of microbial mats meets the constant threat of ice. The Huronian glaciations did not merely cover the Earth with ice, they deeply disrupted the planet's geochemical dynamics. By altering the distribution of ocean waters between ice-free zones and zones locked in ice, they disturbed the great marine balances. Intense glacial erosion carried immense quantities of debris to the seabed, altering sedimentation cycles. Even the dissolution and precipitation of minerals were transformed, giving rise to unique rock strata. These can still be read today in the archives of the Earth's crust. At the end of this long glacial era, Earth emerged deeply transformed. Erosion and sediment deposits reshaped landscapes, opening a new atmospheric chapter. The Huronian glaciations thus mark a key step toward a more stable and oxygen-rich equilibrium. At the very beginning of this period, when oxygen is tentatively trying to establish itself in the atmosphere and surface waters, the microscopic world is undergoing profound upheavals. Imagine an ancient ocean, still largely devoid of free oxygen, but dotted with small, weakly oxygenated pockets. In these limited zones, certain metals and nutrients radically change behavior. Manganese, in particular, transitions from a divalent state, manganese 2+, to a tetravalent state, manganese 4+. This seemingly innocuous chemical transformation marks a turning point. It leads to the formation of the first massive marine nodules. For microorganisms, this change redefines the chemical environment and availability of nutritional resources. Bivalent manganese, initially present in nearly oxygen-free waters, is a very mobile metal. It dissolves easily and circulates freely in anoxic sediments. But as soon as small amounts of oxygen appear locally, an oxidation reaction is triggered, manganese loses 2 electrons. In this new form, it combines with other elements like oxygen or iron, forming solid deposits. These deposits slowly accumulate in crusts or nodules, genuine rounded stones, rich in minerals lying on the seafloor. Their growth is extremely slow, sometimes a few millimeters or a fraction of an inch per million years, but their influence on oceanic chemistry is immense. At this ancient time, the waters contained not only manganese, but also other essential metals like molybdenum, uranium, or vanadium. In the absence of oxygen, these elements remain trapped in sediments, often associated with sulfides. But as soon as the oxygen content increases, even slightly, their behavior changes. They become more mobile. In other words, they are no longer stuck at the bottom, but can dissolve, migrate, and participate in new chemical reactions. Molybdenum, for example, binds with oxygenated compounds and becomes more available for life. Uranium shifts from an insoluble form to a soluble one, making it easier to transport. Vanadium also takes advantage of this oxygenation to circulate more freely in the marine environment. Why do these changes interest the biosphere of the time? Because these trace metals play a crucial role in the functioning of life. The earliest microorganisms, like certain bacteria or microscopic algae, depend on them for their metabolism. Molybdenum is essential for nitrogen fixation, the process that transforms atmospheric nitrogen into usable nutrients. Uranium, although discrete, can influence certain metabolic pathways in trace amounts. As for vanadium, it is involved in chemical reactions in primitive organisms, especially those handling sulfur or nitrogen compounds. Thus, as soon as oxygen becomes slightly more present, these metals become more available, transforming the ocean into a true cultural broth for microscopic life. The formation of these manganese nodules transforms the seabed by creating new microhabitats. Where the ground was once uniform, solid surfaces now appear, formed in concentric layers, serving as a support for entire colonies of microorganisms. Even if complex fauna does not yet exist, certain unicellular organisms are already settling in the cavities or on the asperities of these concretions. Microalgae, similar to future blue-green algae, attach themselves to better capture light. Other bacteria use the available metals for their chemical reactions. A real proliferation of invisible life then unfolds on a microscopic scale. At this time, flora is limited to photosynthetic aquatic organisms, ancestors of cyanobacteria. The arrival of a bit more oxygen stimulates photosynthesis, increasing the production of organic matter. This simple surge is enough to diversify life forms. New metabolic pathways emerge using manganese, molybdenum, or iron. Microbial communities reorganize according to oxygen and nutrient gradients. And this is not just a detail, it's the beginning of a complexity that, much later, will lead to the first structured ecosystems. By observing these dynamics, we better understand the key role trace metals play in the evolution of Earth. The distribution of manganese, uranium, and other elements affects not only the circulation of organic matter, but also the formation of oxides and the organization of microbial ecosystems. Even today, oceanographers analyze the behavior of manganese in modern seas to better understand ancient environments. Geological samples reveal the presence of very ancient nodules, witnesses of an Earth in full transition to a more oxygenated world. By dating them, we trace with precision the steps of this slow chemical mutation. The appearance of these manganese-rich nodules is not a mere geological detail. It marks a real upheaval in the access to marine nutrients, promoting the emergence of increasingly diverse life forms. The microflora, composed of bacteria, unicellular algae, and other organisms invisible to the naked eye, seize this opportunity to refine their adaptation strategies. Some bacteria develop mechanisms to store metals or trap carbon, while others develop enzymes capable of transforming these elements to their advantage. These evolutions, slow or sometimes sudden, contribute to the gradual rise of the marine biosphere. One decisive element in this transformation is the increased mobility of metals like molybdenum and vanadium, both essential to the major biogeochemical cycles. Molybdenum, in particular, plays the role of a cofactor in enzymes that fix nitrogen, a vital process for producing proteins and nucleic acids. When this element becomes more available thanks to oxygen, cell growth accelerates. Thus, biological productivity rises, nutrients circulate more, and a more diverse network of organisms develops. This mechanism triggers a virtuous circle. A little more oxygen makes certain metals accessible. This stimulates microbial life, which in turn can contribute to releasing even more oxygen in its immediate environment. In the long term, these transformations gradually prepare the ground for more complex ecosystems capable of supporting more elaborate forms of life. Future multicellular organisms, including the ancestors of animals, will benefit from this chemically enriched oxygen base, where trace metals become abundant enough to fuel various biochemical processes. The central role of manganese, molybdenum, uranium, and vanadium is part of a series of major evolutionary transitions. At each level of oxygenation achieved, an entirely new field of possibilities opens up for life. In those distant times, the oceans are not yet teeming with animals, plants, or corals, as they will billions of years later. Yet, the ongoing chemical upheavals are already sculpting an underwater landscape, brimming with ecological niches. Diverse microbial communities develop there, notably microscopic flora. As for the fauna, understood here as the very first organisms capable of moving or reacting to their environment, it is still in its infancy. But it already participates in the dynamics of life, exploiting new mineral resources as they become accessible. This transformation of trace metal chemistry does not happen overnight. It unfolds in a slow evolution, guided by the gradual rise of oxygen. Manganese, molybdenum, uranium, and vanadium each play a specific role. The first forms vast mineral nodules, while the others become more mobile and directly influence the metabolism of marine microorganisms. Gradually, this reorganization intensifies, supporting the emergence of an increasingly diverse and complex biosphere. Thus, the formation of manganese nodules and the greater mobility of metals at low oxygen levels mark a key stage, that of strengthening biological productivity in ancient seas. These deposits and nutrients gradually lay the groundwork for future ecosystems. On a geological timescale, these transformations seem slow, but they are decisive for the evolution of many lineages, from bacterial colonies to the first ancestors of complex cells. This chemical reconfiguration thus heralds a major turning point, the emergence of a world where life, nourished by new nutrients and increasing oxygenation, begins to gain in diversity and sophistication. Now, we discover a decisive turning point, the appearance of the ozone layer in the stratosphere, this region of the atmosphere located between 10 and 50 kilometers, 6 and 31 miles in altitude. Before this transformation, the planet was defenseless against certain extreme solar radiation. The ultraviolet type C, among the most destructive, freely struck the surface, making the development of life outside the oceans practically impossible. Then a major chemical change occurred. The oxygen present in the atmosphere began to form ozone. A protective barrier slowly established itself, profoundly changing the fate of the biosphere. To understand how this layer formed and why it was so essential to the emergence of complex terrestrial life, we must return to the key stages of atmospheric oxygenation. In the early stages of this period, the amount of dioxygen in the atmosphere increased slowly, driven by the activity of primitive photosynthetic microorganisms. This dioxygen, composed of two oxygen atoms, gradually managed to remain at high altitudes, despite extreme temperature variations on Earth. In the stratosphere, where the air is drier and more stable than at ground level, the sun's rays behave differently. Up there, despite freezing temperatures sometimes around 50 degrees or 58 degrees or 60 degrees or 76 degrees, the intensity of ultraviolet radiation is much higher. It is in this context that dioxygen interacts with free oxygen atoms, themselves generated by the dissociation of molecules under the influence of UVC. When these atoms encounter oxygen molecules, they can assemble to form trioxygen. Thus, in the upper layers of the atmosphere, the first natural shield against the most dangerous ultraviolet rays is born. Ozone forms a true shield against the most dangerous ultraviolet rays. By filtering these rays, it protects vital molecules like DNA, which carries the hereditary information of organisms. Without this protection, cellular mutations would have been too numerous to allow life outside of water, but as the ozone layer thickened, the harmful radiation decreased at the surface. This allowed the first organisms, notably microscopic algae, to leave aquatic environments and explore other environments. The adaptation was slow, dotted with obstacles, but it initiated the expansion of life on land. On the fauna side, certain forms of life gradually tolerated exposure to the sun on the emerging lands. Microscopic organisms, then larger ones, began to colonize the soils. While they did not resemble our current plants or animals, they laid the foundations of terrestrial biodiversity. The formation of the ozone layer was an essential condition for this expansion. Thanks to it, organisms explored new nutrients in the soils, occupied various ecological niches, and benefited from an air richer in dioxygen, favorable to a more efficient metabolism. The appearance of an ozone-enriched stratosphere contributed to stabilizing the climate by limiting extreme temperature variations that could have hindered the development of species. Meteorological phenomena remained concentrated in the troposphere and still depended on solar energy. But ozone, by absorbing part of the ultraviolet rays, reduced the dramatic warming of the lower atmosphere. The result? Despite the natural fluctuations of solar activity, the surface temperature gradually regulated within ranges more favorable to the emergence of life. The ozone layer acts as a thermal regulator by absorbing part of the solar radiation and limiting its impact in the lower layers of the atmosphere. While other gases also influence the climate, ozone played a key role in blocking ultraviolet rays. Its distribution, facilitated by stratospheric winds and Earth's rotation, allowed for relatively global protection, although some areas were more favored depending on local conditions such as humidity, temperature, or solar activity. The formation of the ozone layer marked a decisive turning point, paving the way for a second great phase of evolution. Less exposed to harmful ultraviolet rays, resistant species were able to breathe air and explore the surface. Simple plants like mosses took advantage of this opportunity to root and perform photosynthesis on moist soils. Although this process took millions of years, it began with the progressive ozone enrichment of the stratosphere. The presence of a protective ozone layer favored the emergence of more elaborate life cycles. Oxygen, now available in greater quantities, allowed multicellular organisms to develop specialized tissues and explore new vital functions. The first forms of vegetation, such as algae, lichens, and vascular plants, began to colonize the soils, supported by less aggressive sunlight. Primitive animals followed this dynamic, benefiting from the new resources offered by these emerging ecosystems. A more stable climate, limited seasonal and geological extremes, providing species with the necessary time to diversify and develop more complex forms of organization. Although glacial or arid periods still existed, the presence of an ozone layer in the stratosphere protected the surface from type C ultraviolet rays, thus avoiding constantly hostile conditions. This moderation of environmental factors was essential for the gradual rise of biological complexity. Without this natural barrier, terrestrial life would undoubtedly have been impossible or limited to a few sheltered aquatic environments. Over the ages, this protective barrier experienced variations, proving that the chemical balance of the stratosphere remains fragile. However, during the period we discuss, it proved fully effective, paving the way for a true expansion of life on land. By significantly reducing type C ultraviolet rays, ozone transformed the planet into a vast open-air laboratory where organisms could explore new habitats. Thus, the enrichment of the stratosphere with ozone not only allowed life to leave the oceans, it created an environment sufficiently stable for more diverse and complex living communities to develop. This moment marks a decisive step in the history of planetary adaptations. When the atmosphere began to slowly enrich with dioxygen, a profound chemical upheaval was triggered. Methane, then produced in large quantities by microorganisms living without oxygen, occupied a significant part of the upper atmosphere. This light gas even played a partial shielding role against certain solar radiation. But with the rise of dioxygen, methane was gradually oxidized into water and carbon dioxide. This conversion altered the composition of the air and disrupted the carbon cycle. It also reduced the overall greenhouse effect, since methane retains more heat than carbon dioxide. The oxidation of methane relies on the reaction between one carbon atom, 4 hydrogen atoms, and dioxygen. This reaction produces carbon dioxide and water. As oxygen became more abundant, this transformation intensified, gradually reducing methane levels in the atmosphere. This change altered the balance of greenhouse gases, leading to a relative cooling of the planet. Although carbon dioxide itself has a greenhouse effect, it was not enough to offset the loss of methane. The first microbial ecosystems thus evolved in air, less reductive, but increasingly oxidizing. The oceans absorbed the excess carbon dioxide, transforming it into carbonate ions that precipitated as minerals. Oxygen, by oxidizing dissolved iron, allowed the deposition of insoluble compounds at the bottom of the seas. All these reactions converted the oceans into effective carbon reservoirs, contributing to the stabilization of the atmosphere over the long term. The increase in oxygen reduced the habitats of methanogens, limiting their capability to produce methane. Although these microbes survived in certain anoxic zones, their planetary role weakened. This led to the emergence of other microorganisms more compatible with the new oxidizing conditions. Isotopic variations in carbon, measured by the ratio between carbon-13 and carbon-12, reveal a major transformation known as the Lomagundi-Gituli excursion. This anomaly, visible in very ancient carbonates, indicates an exceptional accumulation of carbon-13, a marker of global upheaval in Earth's chemistry. Photosynthetic organisms prefer carbon-12. When they die, this carbon remains trapped in sediments, enriching the environment with carbon-13. This modification of the isotopic ratio is visible in the delta-13C measurements. During the Lomagundi-Gituli excursion, the burial of organic matter was so intense that it led to substantial carbon sequestration and increased dioxygen release. Carbon trapped in sediments could not quickly return as carbon dioxide. Meanwhile, the decrease in methane weakened the greenhouse effect, causing slight cooling. The emergence of more oxygenated oceans disrupted the environment of microorganisms. Although multicellular life was still in its infancy, this gradual shift toward an oxidizing world laid the groundwork for future evolutions on the continents. The Lomagundi-Getuli excursion, which lasted several tens of millions of years, represents an unprecedented isotopic anomaly. It reflects a break in the carbon cycle, linked to the decrease in methane and the increased formation of carbonates in progressively more oxygenated oceans. Modern data confirm this phenomenon, now recognized as a crucial milestone in preparing a chemical environment favorable to biological evolution. Atmospheric changes allowed marine microorganisms to diversify. Pioneer bacteria and microalgae thrived in warm waters, producing oxygen through photosynthesis. While some species adapted to the surface layers, others colonized the seafloor. This microscopic diversification was already laying the groundwork for the emergence of more complex ecosystems. Between 2.2 and 2.06 billion years ago, a major isotopic anomaly marked the geological record. The delta-13 carbon, an indicator of the ratio between two carbon isotopes, saw a dramatic increase in carbonate rocks. Typically, isotopic variations of carbon remain moderate, but during the Lomagundi event, they reached very high levels. This reveals a massive burial of organic carbon, preventing its reoxidation. This storage allowed for increased oxygen release, profoundly altering the atmospheric composition. The burial of organic matter limited the return of carbon to the atmosphere, reducing carbon dioxide production. Meanwhile, photosynthesis continued to emit oxygen. This imbalance favored a progressive enrichment in free oxygen, leading to significant chemical and biological upheavals on Earth. Scientists have long analyzed the Lomagundi anomaly to uncover its mechanisms. One of the main hypotheses suggests particularly intense photosynthesis, accompanied by a decrease in organic matter degradation, perhaps related to marine and atmospheric conditions less favorable to respiration. Other hypotheses suggest that tectonic movements may have allowed the burial of this matter in vast sedimentary basins, protecting it from any reoxidation. The chemical composition of the oceans at that time, likely different from today, may have played a key role in how carbon was deposited. A high concentration of reduced iron or other elements could have promoted the preservation of organic matter on the seabed. In parallel, increasingly efficient microbial communities in carbon fixation reinforced this process. These combined factors created ideal conditions for the accumulation of organic carbon, explaining the high levels of delta-13C in carbonate rocks. At the end of the Lomagundi event, delta-13 carbon values dropped sharply, marking the post-Lomagundi crash. This shift reflects a loss of stored carbon or a decline in photosynthesis, reducing oxygen production. The partial pressure of oxygen then decreases significantly, opening a new stage in Earth's chemical history. The decrease in oxygen after the post-Lomagundi crash did not return Earth to its most primitive conditions, but it slowed the rise of oxygenation. This slowdown likely disrupted biological diversification, especially among oxygen-dependent organisms, even if direct fossil evidence remains limited. The Lomagundi event and its abrupt downfall demonstrate the extreme sensitivity of biogeochemical cycles. As long as organic carbon was buried, oxygen could accumulate in the atmosphere. But as soon as this storage decreased, oxygen ceased to progress. This dynamic perfectly illustrates how geochemical balances can overturn. This anomaly did not occur in isolation. It was part of a complex set of interactions between tectonics, ocean chemistry, and the diversification of microbial life. Geological signatures show how unstable the planet's oxygenated balance was. The Post-Lomagundi crash illustrates this sudden shift. This episode highlighted the profound effects of organic carbon burial on the atmosphere and life, paving the way for future transformations. After a transitional phase marked by a sharp rise in atmospheric oxygen, Earth enters what scientists call an intermediate state, located between 2 billion or 2,000 million and 1.5 billion or 1,500 million years before our time. During this period, the partial pressure of oxygen stabilizes at modest levels, estimated at between 1 and 10% of what we know today. In plain terms, the air was much less rich in oxygen, making the emergence of complex animals impossible. During this period, the oxygen level remains too low to sustain a high metabolism in large creatures. Life, therefore, remains mostly microscopic and poorly diversified, confined to marine environments. Cyanobacteria, already active on the surface, continue the slow production of oxygen through photosynthesis. However, this activity remains insufficient to transform the planet into an environment conducive to the emergence of a complex fauna. Free oxygen struggles to accumulate in the atmosphere because it is quickly captured by chemical reactions, notably with sulfur and volcanic origin iron. Additionally, oxygen production is still too slow to compensate for these losses. The balance remains fragile, maintaining a low atmospheric concentration. Meanwhile, the oceans of this era present a stratified organization. On the surface, where sunlight penetrates, the water contains enough dissolved oxygen to host microbial communities and some unicellular organisms. But in deeper areas, where light no longer reaches, the environment remains anoxic. In these zones, iron remains in ferrous form, a very soluble state, creating conditions referred to as ferruginous, characterized by high concentrations of iron in solution. The oceans remain partially oxygenated on the surface, but deprived of oxygen in the depths. This stratification prevents the emergence of complex animals, which need more oxygen to live. The appearance of a diversified fauna is therefore impossible at this stage. Banded iron formations still appear locally in some ancient basins, although they are less abundant than before. These formations alternate layers rich in iron and silica, leaving characteristic red or gray bands. Their presence reflects the persistence of local chemical interactions despite global oxygen stagnation. Sometimes, in the less oxygenated oceans, ferrous iron oxidizes to ferric iron when weak oxygen pockets appear near the surface. These reactions form red or brown bands, characteristic of banded formations. Though rare, these precipitations testify to the minimal yet significant presence of oxygen in the ancient environment. Despite the absence of large animals, microbes proliferate in the oceans, some exploiting surface oxygen, others surviving in anoxic environments. The first eukaryotes slowly emerge, utilizing the limited available resources. While global temperatures are temperate, a few glaciations punctuate this era. Between 2 billion or 2,000 million and 1.5 billion or 1,500 million years, Earth goes through a stable phase, with no significant rise in oxygen levels. This is referred to as oxygen stagnation, which limits the evolution of the biosphere and slows the emergence of more complex life forms. The stability of oxygen in the atmosphere holds due to a fragile balance. While photosynthetic organisms produce it, volcanoes and sediments consume it immediately. The reducing gases released by volcanic activity and sediments, rich in compounds trapping oxygen, keep this gas at low levels. This chemical lock prevents oxygen from reaching higher concentrations, thus blocking the emergence of more complex life forms. Since the production of dioxygen began on Earth, microorganisms have had to face a new challenge: the toxicity of oxygen. By reacting within cells, dioxygen generates highly aggressive compounds, known as reactive oxygen species, capable of damaging membranes, altering proteins, and even causing DNA mutations. To survive, the first microbes, lacking a nucleus, developed enzymatic defense systems, such as catalases and peroxidases, responsible for neutralizing these toxic compounds. These adaptations were not merely biochemical solutions. They marked the beginning of a true evolutionary race. Only organisms capable of defending themselves effectively could thrive in an increasingly oxidizing world, thus starting a metabolic diversification that paved the way for the complexity of life. Long before the emergence of nucleus-bearing cells, life was based on prokaryotes. These are organisms whose genetic material floated freely in the cytoplasm. Exposed to reactive oxygen species, these primitive microbes had to develop vital defense mechanisms. In addition to catalases and peroxidases, they developed superoxide dismutases, capable of converting aggressive compounds into more stable molecules. Only the lineages that managed to protect themselves effectively survived the rise of dioxygen. Gradually, some even learned to take advantage of this oxygen. This is where cytochromes come in, proteins equipped with a ferrous cofactor, essential for electron transfer in aerobic respiration. This innovation allowed a major energy gain, particularly in ATP production, the key molecule for cellular energy. Having such a metabolic advantage enabled these organisms to occupy new environments and paved the way for more complex biodiversity. Concurrently, the rise of dioxygen transformed the chemistry of natural environments by making certain metals, like iron or molybdenum, more mobile and available. This facilitated access to essential cofactors for creating new enzymes. In this enriched context, the very first eukaryotes, the protists, found a conducive environment for their development. Thanks to their internal organelles, these cells were able to exploit cellular respiration, where dioxygen serves as the final electron acceptor. This process offered them a crucial energy gain, facilitating their reproduction and expansion. The abundance of oxidized metals broadened their enzymatic palette, making their metabolism more flexible and efficient. Cytochromes became more refined, making respiratory chains more effective, while new catalases and peroxidases limited the damage caused by reactive oxygen. Thanks to this environmental and biochemical advancement, protists colonized a wide variety of habitats, from coastal waters to deeper zones. This diversification marks a decisive step in the history of life. It prepares the emergence of more complex eukaryotic lineages, the very ones that would later shape the biosphere. Subduction plays a key role in the oxidation of the Earth's mantle. As it sinks into the depths, it transports rocks, minerals, and sediments rich in chemical or biological elements. These materials, subjected to high pressures and temperatures, react with the upper mantle. This interaction triggers profound chemical transformations that durably influence the Earth's composition. This episode marks a major turning point in the geochemical evolution of the globe. In this subduction process, a key element comes into play: the introduction of oxidized compounds. Sulfate, to simplify, is a group with a sulfur atom bonded to 4 oxygen atoms, negatively charged. When sediment loaded with organic matter and metals enters the subduction zone, the temperature climbs, sometimes beyond 800 degrees Celsius or 1,472 degrees Celsius, and the pressure becomes enormous. Under these extreme conditions, certain minerals decompose, releasing ferric iron and sulfur. This sulfur is then transformed into compounds like sulfate, which can descend even deeper into the mantle. The transport of oxidized compounds in the mantle increases the chemically available oxygen, not in the form of free gas, but integrated into minerals. This oxidizing level is measured by the oxygen fugacity, a key indicator. To evaluate it, geologists use a reference called the FMQ buffer, based on an equilibrium between phayolite, magnetite, and quartz. Above this threshold, the mantle is more oxidizing. Below, it is more reducing. The gradual addition of oxidized sediments through subduction has slightly increased the mantle's oxygen fugacity, shifting from levels close to the FMQ buffer to FMQ+1. This change has enriched certain areas with oxidizing elements, pushing chemical equilibriums towards the formation of minerals richer in ferric iron and oxygen. This enrichment in oxidized elements is not simply a geological matter. It directly influences the nature of gases released by volcanoes, which are true energy drivers of our planet. When the mantle becomes slightly more oxidizing, volcanic fluids, lavas, and plumes contain fewer reducing gases, such as carbon monoxide or dihydrogen. Thus, the atmosphere gradually receives fewer compounds capable of consuming oxygen. This is a form of positive feedback. The more oxidized the mantle, the less the atmosphere is depleted of dioxygen, which facilitates its accumulation on a planetary scale. The gradual evolution of the atmosphere and hydrosphere towards a more oxidizing state, although spread over millions of years, proves crucial for the ecosystem. This new environment opens the way for life forms capable of exploiting aerobic respiration, much more efficient than fermentation or sulfur usage. In the microbial world, this allows for better decomposition of organic matter. The first terrestrial life forms, mainly prokaryotic cells, then simple eukaryotes, begin to diversify their structure and explore new ways of using energy. Even though multicellular organisms will only emerge later, the foundations of this complexification are already being laid in oceans and on shores, partially exposed to air. At this stage, mineral-rich oceans and a slightly oxygenated sky provide a conducive environment for microbial innovation. Life learns to exploit nitrogen in various forms to make its vital components. The nitrogen cycle then takes place, with fixation, nitrification, and denitrification as biochemical pillars. In this context, the atmosphere is not completely devoid of oxygen, but it contains too little to sustain complex life. It does, however, offer enough to allow an essential process, nitrification. This mechanism transforms the ammonium ion, resulting from the degradation of organic matter or nitrogen fixation, into nitrites and then nitrates. Specialized bacteria feed on them, deriving the vital energy from this conversion for their development, while producing compounds useful to other organisms. This process relies on an oxidation reaction requiring a slight presence of dioxygen. The responsible bacteria, notably proteobacteria, use complex enzymes to extract electrons from ammonium and transfer them to other molecules. This mechanism generates water and releases nitrate, an oxidized form of nitrogen. The appearance of this nitrate stimulates the first marine ecosystems, particularly photosynthetic organisms, and promotes the diversification of food chains. In parallel, another process gains importance, denitrification. This reverse reaction transforms nitrate into gases like nitrogen monoxide, laughing gas, or dinitrogen. It takes place in low oxygen environments, such as marine sediments or stagnant waters. There, in depth, specialized microbes return some of the nitrogen to the atmosphere in gaseous form, thus contributing to the overall balance of the nitrogen cycle. In a world where dioxygen begins to diffuse into the oceans and atmosphere, the balance between nitrification and denitrification remains unstable. The former depends on a constant oxygen supply, while the latter thrives in low oxygen environments. The weak ocean circulation and nascent geological architecture create a stratified sea with slightly oxidized surface waters above anoxic deep layers. This separation gives rise to hybrid ecosystems, some centered on oxygen, others on its absence, all linked by successive transformations of nitrogen. The enrichment of surface waters with nitrates promotes the development of algae and photosynthetic bacteria, which, better nourished, produce more organic matter. This dynamic strengthens the foundations of the biosphere and prepares the emergence of more efficient nutrient cycles. Nitrification also extends to transitional zones such as estuaries, where freshwater and saltwater create gradients favorable for microbial adaptation. These communities alternate between nitrification and denitrification according to microenvironments, ensuring a constant recycling of nitrogen. Meanwhile, deep oxygen-deprived zones remain major hubs for denitrification. When organic matter descends to the sediments, its degradation consumes local oxygen, creating an anoxic environment ideal for microbes. These microbes then use nitrate ions as electron acceptors, releasing various nitrogen gases. Even isolated, these deep regions play a crucial role. They ensure the continuity of the nitrogen cycle by balancing the exchanges between its oxidized and reduced forms. The slow increase of dioxygen fosters the emergence of new ecological niches where these processes unfold. At every level, microbes adjust their strategies to exploit nitrogen according to their needs. This fragile balance already heralds the complexity of future ecosystems. By providing regular access to nitrate, the planet sets the stage for a robust and diverse biodiversity. Throughout Earth's history, the gradual rise of dioxygen in the atmosphere profoundly changed the living conditions for microscopic beings, especially prokaryotes. These organisms, whose cells do not have a nucleus, are distinct from eukaryotes. Many of them thrived in an environment initially devoid of oxygen, a milieu relatively spared from the effects of oxidation. But as dioxygen spread, it became a toxic agent for some microbial communities. This change triggered an unyielding natural selection, profoundly altering the diversity of prokaryotes. Among the major losers of this transformation were planktonic methanogens, aquatic microorganisms that produce methane. Plankton refers to the ensemble of organisms that float or drift in water, unable to swim against the current. These methanogens thrived in oxygen-free environments, where they drew energy by transforming carbon compounds into methane. But with the increase of dioxygen in the environment, their survival was compromised. This highly reactive gas disrupted their cellular processes, quickly becoming toxic. Many of these communities then disappeared or withdrew into anoxic areas, far from the growing influence of oxygen. However, some prokaryotic groups managed to adapt to this new order by developing remarkable strategies. Cyanobacteria, also known as blue-green algae, diversified by taking advantage of their tolerance to sunlight and the presence of oxidants like dioxygen. Despite their name, these algae are not true algae, but photosynthetic bacteria without a nucleus. Microscopic yet decisive, they played a key role in oxygen production through photosynthesis. As oxygen concentration increased, only species capable of withstanding the light intensity and oxidative environment could survive, paving the way for increasingly advanced lineages. A key phenomenon of this era is horizontal gene transfer, an exchange of genetic material between organisms outside of traditional reproduction. Unlike hereditary transmission from parent to offspring, this mechanism allows for the rapid acquisition of new functions by integrating genes from other lineages. In a world undergoing oxygenation, this ability was crucial. Genes related to the detoxification of reactive molecules derived from dioxygen, capable of damaging membranes, proteins, and DNA, circulated among diverse prokaryotic groups. Possessing enzymes to neutralize these reactive species proved vital. Thanks to this genetic transfer, some microbes acquired antioxidant defenses, significantly improving their survival in an environment that had become toxic for others. The toxicity of dioxygen arises from its ability to react with numerous cellular components, generating highly harmful byproducts. Among them, hydrogen peroxide can oxidize biological structures and cause irreversible damage. To counteract this, several key enzymes have appeared or spread through horizontal transfer. Such is the case with catalase and superoxide dismutase, which neutralize hydrogen peroxide and the superoxide anion, respectively. By protecting cells against these oxidative attacks, these enzymes have provided a vital advantage, allowing some organisms to explore slightly or heavily oxidized environments. This evolutionary dynamic not only strengthened resistance to dioxygen, but also altered interactions among prokaryotes. Some, better equipped against oxidation, rapidly colonized diverse environments, illuminated surface waters, shallow sediments. In these areas, they formed microhabitats shared with less robust species, which indirectly benefited from their presence. Thus, beyond simple coexistence, metabolic collaborations and genetic transfers multiplied, weaving a network of complex exchanges. This interconnection accelerated adaptation to an increasingly oxygenated environment and stimulated the diversification of prokaryotes. The cyanobacteria, already mentioned, likely benefited from gene transfers that strengthened their protection against oxidative stress and improved their photosynthesis. These adjustments allowed them to withstand high light intensities while limiting damage related to excess oxygen. Producing dioxygen themselves, they had to avoid a form of self-intoxication. To this end, they developed various mechanisms, screening pigments to filter light, enzymes capable of repairing damaged structures. Horizontal transfer facilitated the integration of more efficient enzymes, giving a clear evolutionary advantage to some lineages. These genetic exchanges likely occurred not only among cyanobacteria, but also with other prokaryotes in the same ecosystem. Over time, the pressure exerted by dioxygen favored the emergence of more complex, resistant, and interconnected life forms. We arrive at the 23rd stage of this documentary journey. Here, we will explore how energy stored over the ages has shaped the oxygen content of the atmosphere. We will unveil numbers and estimates that, under their apparent austerity, tell a fascinating story. About 2 billion years ago, the primitive biosphere had already produced more than 1021 moles of dioxygen. This colossal figure illustrates the extraordinary ability of early organisms to release this vital gas through photosynthesis. At the time, microbial communities, akin to cyanobacteria, played a central role. They captured solar light, split water, released dioxygen, and synthesized organic molecules essential for their growth. Even confined to aquatic environments, still hostile to complex life forms, these microbes were already profoundly transforming planetary chemistry. To grasp the magnitude of this number, one must understand what a mole is. In chemistry, a mole corresponds to a fixed number of particles. here dioxygen molecules. More precisely, it contains about 6.022 x 1023 units, a value known as Avogadro's number. In other words, the quantities mentioned far exceed what can be conceived at the molecular scale. In reality, the accumulation of dioxygen recorded in certain geological archives is immense, even on a planetary scale. Such a volume of dioxygen was not formed all at once. It results from a balance between inputs, called sources, and removals, the sinks. The sources mainly refer to photosynthetic microorganisms capable of transforming light, water, and carbon dioxide into dioxygen and organic matter. The sinks include processes that consume or trap this oxygen. Among them are the oxidation of iron-rich minerals, reactions with sulfur, burial of organic matter, or interactions with reductive volcanic gases from Earth's interior. Iron, sulfur, carbon, and these gases thus long slowed the stable accumulation of dioxygen in the atmosphere. Let's take the example of iron-bearing minerals present in ancient oceans. When dissolved iron encountered oxygen, it oxidized, forming hydroxides and oxides that fell to the sea floor. Thus, a significant portion of the oxygen produced by the biosphere was immediately used to oxidize iron before it could permanently join the atmosphere. This trapping phenomenon greatly limited the oxygenation of the air despite photosynthesis. The same principle applied to sulfur and certain volcanic gases, which were also capable of consuming oxygen. This helps us understand the concept of balance. On one hand, sources released oxygen. On the other, sinks immediately absorbed it, slowing its rise in the atmosphere. Beyond the chemical aspect, these oxidation dynamics already impacted life. The first organisms, whether photosynthetic or not, had to adapt to environments where oxygen availability varied locally. Certain microbial species, tolerant to low concentrations, occupied specific niches, while others, more sensitive, settled in slightly better oxygenated areas, such as shallow coastal margins. This uneven distribution of oxygen influenced the distribution of the earliest life forms, which were essentially unicellular. Yet, despite their apparent simplicity, these microorganisms were already laying the groundwork for the evolution of future multicellular beings. Today, to measure the progress made, it is useful to compare the historical production of oxygen with the amount currently present in the atmosphere. This amount is estimated to be about 3.7 x 10^20 moles, or approximately 3.7 x 10^20 lb mole. An impressive figure, but still less than all that has been produced, captured, or stored over the past 2 billion years. Why this discrepancy? Because the stable concentration of oxygen we breathe only reflects a portion of what has been generated. A large quantity has been trapped in soils in the form of iron oxides or oxidized sulfur compounds, limiting its accumulation in the air. Moreover, as the biosphere evolved towards larger and more active organisms, respiration intensified, altering in turn the ambient oxygen balance. In reality, oxygen has always been at the heart of a cycle of feedback. Over the ages, photosynthetic productivity increased or decreased, influencing the amount of available oxygen, which in turn could stimulate or slow down certain biological processes. During cold periods, the metabolism of numerous microorganisms slowed, reducing oxygen production. In contrast, strong volcanic activity released reducing gases that hindered its accumulation. This constant interplay between sources and sinks shaped a fragile balance essential for the emergence of more complex ecosystems. It must be kept in mind that these estimates, whether it be the cumulative production of oxygen or its current stock in the atmosphere, are not fixed. They rely on models, calculations, and geological data that are constantly evolving. Scientists rely particularly on the isotopic composition of ancient rocks, the presence of oxidized minerals, or the distribution of certain chemical forms of sulfur and iron. These true chemical fossils reveal how oxygen circulated or was trapped in ancient times. With the advancement of techniques and field discoveries, estimates become more precise, but the orders of magnitude remain solid, confirming the magnitude of the processes at play. In summary, this energy and molar balance reveals an essential point. Long before the appearance of complex animals or modern plants, ancient microorganisms had already transformed the planet's chemistry. The data show that the Earth was moving towards an oxygen-rich atmosphere, even if this gas was largely consumed or stored in inert forms. For the biosphere, this slow evolution toward an oxic air allowed major innovations, such as aerobic respiration, which is far more efficient than the then-dominant metabolic pathways. This ability to exploit oxygen ultimately made possible the emergence of a complex fauna and flora, up to the diversity we know today. More than 2 billion years before our era, Earth began transitioning to an oxygen-rich atmosphere. This change directly impacted the continental crust, giving rise to landscapes tinged with bright red. This color comes from hematite. It was during this time that the first hematite-rich red sandstones appeared, true markers of a world in transition. These sandstones formed when the atmosphere contained enough oxygen to oxidize the iron within sediments and emergent rocks. Until then, iron remained in a reduced form, induced no red coloration. Exposed to a more oxidizing environment, it transformed into hematite, a much more stable mineral on the surface. This geochemical shift profoundly reshaped the planet. This atmospheric transition also altered the chemical balance of the Earth's crust. Iron wasn't the only element to oxidize. Uranium also saw its behavior change. This metal can exist in multiple oxidation states. In an oxygen-poor atmosphere, it remained mostly in the +4 form, which is not very mobile. But with the increase in oxygen, it transformed into a +6 form, which is much more soluble. This transformation allowed uranium to migrate over long distances, carried by groundwater and rivers. Over time, this increased mobility led to its concentration in certain sedimentary basins, where uranium-rich conglomerates formed. These cemented rocks contain a variety of fragments: gravel, sand, and sometimes fossil remains of plants or animals. In these conglomerates, oxidized uranium can precipitate if it encounters a reducing environment or binds to certain minerals. Over time, this leads to the formation of rich uranium deposits. For geologists, these formations are valuable markers. They prove that, at the time, oxygen was already present enough to render uranium soluble, then concentrate it locally. But the consequences of this redistribution aren't just mining-related. They also signal the Earth's entry into a phase of more active surface chemistry. Shallow oceans, rains, and rivers now interacted differently with altered rocks, promoting the circulation of substances essential to life. Microbial ecosystems, for example, could benefit from the increased availability of nutrients. The hematite-rich red sandstones also provide clues about the stability of the Earth's crust. When a mineral oxidizes, it often becomes more resistant to erosion. Hematite, for example, forms a protective layer on sand grains and rocks, limiting the effects of water, wind, or temperature variations. At the time, these variations could be pronounced depending on the regions, between hot and humid or dry and continental climates. The geological formations rich in iron oxides acted as shields. The rocks cracked less, and the soils that developed on them offered an ideal refuge for microorganisms, the first links in food chains. For the still rudimentary flora of the time, the presence of more stable soils was an advantage. Even though stem or seed plants didn't exist yet, mats of algae and colonies of photosynthetic microorganisms could anchor themselves solidly. This favored the formation of biological mats, which in turn stimulated oxygen production and the fixation of minerals in sediments. But this stabilization had not only biological effects, it also influenced geological architecture over the long term. Entire continents saw their sediments consolidate, limiting erosion. In a world still marked by tectonics and meteoritic impacts, the continent's ability to maintain their thickness shaped the coasts, river basins, and the distribution of life-favorable habitats. Meanwhile, the accelerated oxidation of uranium contributed to reshaping the geochemical landscape. Groundwater, by carrying more uranium and other elements from rocks, enabled the formation of new soils and the accumulation of metals in previously poor areas. This circulation also enriched the waters with dissolved nutrients, essential for the development of microorganisms and later, more complex plants. Over time, oxidized rocks became more capable of trapping these elements in a stable matrix. Iron oxides retained trace metals like molybdenum or vanadium, which would be released later under favorable conditions, nourishing the burgeoning biosphere. Earth then became an interactive system where the soil played an active role in the dynamics of life. For researchers, the study of hematitic red sandstones and uraniferous conglomerates remains essential for tracing events that occurred after 2 billion years. Observed in outcrops or drillings, these geological clues reveal the close links between soil chemistry, tectonic activity, and the evolution of early living communities. During the Meso-Paleoproterozoic era, Earth enters a transitional phase where oxygen becomes more present in the atmosphere. This gradual change sets the stage for the Neoproterozoic oxidation, a major event in Earth's history. While marine microbes thrive, the continental soils show signs of chemical transformation. The slow but continuous increase in oxygen forces the life forms of the time, mainly microbial, to adapt. Although this element is essential for life, it also poses a threat to certain organisms with metabolisms still suited to an oxygen-poor world. At this time, the sulfur cycle relies on biochemical reactions, where some organisms transform sulfate into sulfide to produce energy. This sulfide stabilizes by binding with metals or depositing in sediments. This process previously maintained a balance. However, the increase in oxygen gradually limits these deposits, favoring oxidation reactions. This new dynamic hinders the proliferation of sulfide-producing bacteria and decreases the concentration of reducing gases in the atmosphere, marking the emergence of a new equilibrium in the oceans. In the Meso-Paleoproterozoic, atmospheric oxygen is increasing slowly. Tectonic changes and volcanism reduce the release of reducing gases, thus decreasing Earth's consumption of oxygen. Photosynthetic organisms, such as planktonic algae, produce more of it, causing a slow accumulation in the air. Although this concentration remains insufficient for complex life, it initiates a major environmental transformation. This subtle yet constant process prepares the planet for future upheavals, which will make the emergence of more elaborate organisms possible. The chemical transformations related to oxidation directly affect the oceans. Dissolved iron more easily transforms into oxides that deposit in shallow areas, coloring the seafloor. Trace metals become more available in their oxidized form, paving the way for new metabolisms in microbes. This dynamic stimulates a gradual diversification, although life still remains limited to simple structures. These evolutions lay the foundation for marine ecosystems capable, in time, of supporting richer and more complex life. The increase in dioxygen gradually reaches critical thresholds, called tipping points, necessary for the emergence of complex tissues and multicellular life. At this time, life forms remain confined to aquatic environments, as the ozone layer is still too thin to filter ultraviolet rays. However, the slow accumulation of oxygen in the atmosphere gradually allows the formation of this protective layer. Once sufficiently developed, it paves the way for a future colonization of dry land by organisms capable of freeing themselves from the marine environment. The Neoproterozoic oxidation events, NOE, mark a significant rise in atmospheric oxygen levels. They coincide with a diversification of life, notably the appearance of multicellular forms visible to the naked eye. Even before complex animals, structures grouping multiple cells form, initiating a transition towards organized and specialized organisms. This context also favors new reproductive strategies in which embryos need more oxygen to develop. In ancient oceans, vast mats of algae and bacteria produce oxygen while recycling nutrients. Small, primitive creatures feed on organic matter from sediments. The gradual accumulation of oxygen gradually allows the emergence of aerobic respiration, which releases more energy. Thanks to this new source, slightly more complex life forms emerge, such as cellular colonies in the shape of discs or tubes. These stages announce the preparation for a more marked biological evolution. Neoproterozoic oxidation marks a major turning point, even if its implementation remains gradual. The increase in photosynthesis, the reduction of reducing gases, and the evolution of sulfur cycles together contribute to enriching the atmosphere with oxygen. This process still remains insufficient to support complex life forms, but it paves the way for a decisive transformation. When conditions are met, Earth will be able to host an explosion of diversity. Life stands ready to reach a new level.